Welcome to Cheenta Statistics and Data Science. Today we are going to solve this problem from CMI Data Science 2022, problem number 6 and 7. So let's start with problem number 6. So this problem says a matrix C is said to be symmetric if C transpose is equals to C. Which of the following is or are true? Let A and B be n cross n matrices. So there are four options. We have to check which of them are true and false, and yeah. So the first one says if A is symmetric and invertible, then A inverse is also symmetric and invertible. So let's check that. So A is symmetric, that means A is equals to A transpose, right? And A inverse exists because it is said that A is invertible. So A inverse exists. So these are the information given. So therefore A inverse into A is equals to I, right? The identity matrix. Therefore A is the inverse of A inverse, right? A itself is the inverse of A inverse. That means A inverse is equals to A. That means A inverse is invertible, right? And about the transpose, see, the transpose of the inverse is actually nothing but the inverse of the transpose, right? So it is actually again A transpose is A, so it ultimately it is A inverse, right? So A inverse is symmetric. Therefore, option A is true. Okay, option A is true. What about option B? If A and B are symmetric, then C is equals to AB is also symmetric. Let's check that. So A transpose is equals to A and B transpose is equals to B because they are said to be symmetric. Now given C is equals to AB, C transpose is equals to AB whole transpose, right? Which is B transpose into A transpose. From the properties of transpose, we know that, which is B into A because B transpose is equals to B and A transpose is equals to A already given. So, but BA is not equals to AB, right? So it is not equals to C. Therefore, C transpose is not equals to C, right? Therefore, C transpose, since C transpose is not equals to C, therefore C is not symmetric, right? So option B is not true. Option B is not true, right? What about option C? It says if A and B are invertible, then C is equals to AB is also invertible, right? See, A and B are invertible. That means A inverse and B inverse both exist. Given C is equals to AB, let D is equals to B inverse into A inverse. We can, it is defined, right? Because A inverse and B inverse both exist. So let us define D to be B inverse into A inverse. So C into D is nothing but AB into B inverse into A inverse, which is nothing but I, right? Because this B into B inverse becomes I, and then A into A inverse becomes I. So ultimately it is I. So that means C into D is actually equals to I. Therefore, D is actually nothing but the inverse of C. That means B inverse into A inverse is the inverse of AB, right? So AB is invertible. So option C is also true, right? Option C is true. Very easy problem. Now, lastly, option D. If A and B are symmetric, then D is equals to A plus B is also symmetric. Let us check that. So A transpose is equals to A and B transpose is equals to B, right? So D is equals to A plus B. So D transpose is nothing but A plus B whole transpose, which is A transpose plus B transpose, which is equal to A plus B, right? Because A transpose and B transpose are respectively A and B, right? So A plus B, which is equal to D. Therefore, D transpose is equals to D. Therefore, D is symmetric, right? So yeah, option D is also true. So among these four options, only option B is not true. The rest, option A, C, and D are all true, right? So yeah, there you have it. Very easy problem, right? Or you only needed to know the properties of transpose and inverse. That's it. Very easy problem. So let's move to the problem number 7. So problem says that which of the following statements is or are true? Let A be an n cross m matrix with n less than m. Then there is a non-zero solution y with ay equals to 0 only if A has full row rank. Let's check that. See, here it is given that A is an n cross m matrix where n is less than m, right? Now, A into x is equals to 0. These are vectors. A into x vector is equals to 0 vector has a non-zero solution if and only if the rank of the matrix A is less than the number of columns, right? Therefore, since the system A into y is equals to 0 has a non-zero solution if and only if the rank of A is less than m, sorry, less than m, right? The number of columns here. Now, since already rank of A cannot be more than m, right? Because we know that the rank of A is less than equals the minimum of both the row number and the column number. Since already n is less than m, therefore rank of A is less than equals n, right? Which is already less than m, right? Therefore, even if rank of A is less than m, strictly less than n, right? Even if it is strictly less than n, which is the number of rows, that means even if the rank of A is not equal to the row, that means even if the A is not full row rank, it still has a non-zero solution, right? So the condition of only if is not required. If it is full row rank, then fine. But even if it is not full row rank, it still has a non-zero solution. So option A is false because it is said that only if A has full row rank, there is going to be a solution to this. There's going to be a non-zero solution. But no, even if it is not full row rank, it's still going to be have a solution, non-zero solution. Yeah. So option A is not true. What about option B? Let A be an n crossing matrix with n greater than m. Then there is a non-zero solution y with ay equals to 0. Right. The same question, similar question. N is greater than m here. So A is an n crossing matrix where n is greater than m. Again, there is a non-zero solution of ay equals to 0 if and only if rank of A is less than m, right? The number of columns. Now, here, rank of A is less than equals m, right? Less than equals m, because obviously, again, the rank of A cannot is strictly less than equals the minimum of both the row number and the number of rows and the number of columns. Minimum of n and m, right? So rank of A is less than equals m because here m is the smaller one. So obviously it is less than equals m, which is less than n. Therefore, there may or may not be a non-zero solution, right? Because the rank of A is less than equals m, right? So here it is given. See, here it is given that there is a non-zero solution. It is implying that there is a non-zero solution. So non-zero solution is only existing if and only if the rank of A is less than m, right? Less than less than the number of columns. Now here we know that it is less than equals m. It can be, there is a possibility of a rank of A equal to being equal to m, right? There is a possibility. It is not strictly less than m. So there may or may not be a solution, non-zero solution. So we don't know which one it is. So again, option B is not true. What about option C? The row rank of an n cross m matrix is equal to its column rank only when n is equals to m. The row rank of an n cross m matrix is equal to its column rank only when n is equals to m. So basically, it says that the row rank and column rank of a matrix equal to each other only when the matrix is square matrix. But no, it's actually not not true because for any matrix A of order n cross m, any matrix of any order, the row rank of A is equals to the column rank always. It doesn't necessarily have to be a square matrix; it can be a matrix of any order. So comes from theory. The row rank of any matrix is equal to its column rank. So it doesn't necessarily have to imply the condition that A has to be a square matrix, right? So option C is also false. Now what about option D? Let A be an n cross a matrix. Suppose A is equals to B into C, where B has size n cross R and C has size R cross n. Then the rank of A is less than or equal to R. So A is already an n cross n square matrix, and A is equals to BC, where B is of n cross R and C is of R cross n, right? And it is said that the rank of A is less than equal to R. See, A is this, right? N cross n into B is equals to B into C, where B is n cross R and it's R cross n. Now, rank of A is nothing but rank of BC, right? Because A is equals to BC. Now, this is less than equals rank of B because we know the rank of the product is less than equals the rank of the individual matrices is less than equals rank of, so rank of BC is less than equals rank of B. Now, rank of B is actually less than equals R because it is both less than equals n and R, right? The rank of any matrix is less than equals both of its number of columns and number of rows. So it's less than equals R. It's also less than equals n, but here we need R. So rank of B is less than equals R. Therefore, rank of A ultimately rank of A is less than equals R, right? So here we got it. So yeah, option D is true. So only option D is the only one true here. The other options are false. A, B, C are all false, and option D is the only one which is true here. So yeah, there you have it. The solution to this problem. It was a very easy problem actually. You only needed to know the basic properties of the systems of equations and all that. It's very easy. So yeah, there you have it. So do like, share, and subscribe to the channel for more exciting problems. See you till next time.